between shear force diagram and bending moment is this, okay? So in terms of magnitude, or so this is the shear force, right? So in the shear force, by looking at the magnitude, okay, so you can have positive, right, magnitude or negative magnitude, right? In the bending moment diagram, it will affect the gradient, right? If it's positive magnitude, the gradient is positive. Is negative magnitude, the shear force is negative, the bending moment will be negative. So let me show you. Okay, let me show you. So in this region down here, right, the magnitude is what? Negative, right? The gradient is also negative, right? So if I were to draw a tangent on this curve, right, it's also what? Negative, right? Then over here, what you can see down here, in fact, this will be a better example, right? This region, the gradients are all what? Positive magnitude. So the bending moment, okay, so the bending moment over here will have a positive gradient. You can see this gradient down here is all positive. Okay, so that's a relationship. Then another relationship that you can see when the shear force is equal to 0, when V is equal to 0, there is a possibility that bending moment is maximum or minimum. Okay, so at point 8, we have a minimum. At 2.4, okay, at a 2.4 where intersect, the shear force, the bending moment is as maximum at 48, right? And then it comes to 0, down here is 0 again, as you can see, okay? Now, to interpret the bending moment diagram, okay, what does positive bending means and what does negative bending moment means? So it all depends on the deformation pattern. Okay. Positive bending moment means the deformation pattern will be smiling face. Negative bending moment means the deformation pattern will be what? Sad face. Okay, so this you have to remember. Okay, so this is a very quick revision of the shear force and bending moment diagram. So now the question for us is this. Okay, we still have to determine the principal stresses, and we have not done anything yet. Okay, so what are the points we are going to look at? Okay, so we are going to select. Okay, there are 3 points that I don't know which is maximum. I don't know which one is the maximum. So we have to check. Okay, we have to test. So the first point I'm going to use where x is equal to where z is equal to 0.8 meters, right? At that point, what we have is we will have v, right? We have v is equal to 80 times 10 to the power 3, right? Newton. And we have our moment is equal to minus 16 times 10 to the power 3 Newton meter. Why I select this point? Because that is the point where maximum shear force occur. Okay, this is where maximum shear force occur. Right. Then the next point that I would like to choose is Z is at 2.4. Right. Why I like to select Z is equal to 2.4? Because V is equal to 0 but my moment is at its maximum of 48 times 10 to the power 3. Okay, it's at its maximum of 48 times 10 to the power 3 Newton meter. Okay, and then the third point that we have to check is where Z is equal to 3.2 meters. Why? Because our shear force is equal to minus 40 times 10 to the power 3. And our moment is equal to what? 32 times 10 to the power 3 Newton meter. Okay. So the first point is very obvious, maximum shear, right? The second point is maximum bending moment. The third point is they have two very balancing effect on shear force and bending moment. Okay, so we have identified our points to check. Okay, so now I'll bring this diagram back. Okay, and then I'll take these values. Okay, so these are the values, right? So the first point, I'm going to put my element. So we're going to put our element or points of interest will be along this line. Okay. So this is where Z is equal to 0.8. And then Z is equal to 2.4, somewhere around here. Z is equal to 2.4. And then finally, Z is equal to what? 3.2. So for now, we know that possible failure can occur at these 3 points. Okay, we know that. Now the next thing, so this is what we call macro scale failure analysis. Okay, we know you occur along those three points. Okay, now next we are going to look at micro scale failure analysis. So for this case, okay, we look at the cross section now. Okay, we look at the cross section, right? And failure will occur at this point. Okay. Now, some of you might say, Eugene, why failure will occur over there? Now, if we were to sketch, okay, yeah, I'm going to change this to a graph mode. Okay, if we were to sketch if we were to sketch the distribution, okay, so if I'm to sketch our so if I'm going to sketch, so this this will be our normal stress, and this will be our y distance, right? And this can also be our shear, right? So if I'm going to sketch, right, maybe I should do it a bit bigger. Wait. Go on. bigger some more. Then you can see better. Yep, this is good. Okay, so I have to adjust the failure region. Okay. Okay. So I know I have some words down here. I'll just shift them. Okay, feeling this. So if we were to sketch the bending moment distribution, it will look like this. Okay, again, this is just a sketch. Okay. So this equation, it complies to stress Z is equal to mx over Ixx multiplied by y. Now, if we were to sketch the shear force, it will look like this, right? It will do this. It will go straight. Then it will do this, right? And then it will do this, right? And then it will come down. So this is our shear stress distribution profile. And this is our normal stress, okay? If we pick at the centroid, so at the centroid, this is where this line is where it's our centroid. It's not a very good position. Why at the centroid, stress, normal stress is equal to 0. Over here, tau is equal to tau max. No good. But if we put at the failure region over here, your normal stress is not the highest, right? However, your shear stress also has a certain value. So this region we're going to pick, okay? And we cannot pick at the surface because shear stress is equal to what? 0, okay? So we pick at the failure region where you have a combination of normal stress and shear stress. And what is more interesting is over here, right? You will see, or bottom down here, you will see a radius, yes or no? And this radius is going to be, will cause stress concentration, which I will not teach in this class. You will learn in 303. However, you have to do the analysis from here first, then you put the stress concentration factor. Okay, so over here, in this course, I'm not going to teach you stress concentration factor. I'm going to indicate for you what region that you have to calculate your stress. So for all the stress state we're going to calculate what's happening at the failure region. Okay, so you can see we have found that failure can occur at 0.8, 2.4, 3.2. Microscale, it can occur at where? It will occur where the intersection between the flange and the web, right? So this is the flange, the intersection between the flange, and this is our web. Okay, this is real engineering problem now. Okay, right. So from here we know the values. Okay, we are going to calculate. So we are going to pick one. Okay, I'm going to pick a combination. Okay, I'm going to pick where z is equal to 0.8 first. Okay, so z is equal to 0.8, and at that point your v is equal to 80 times 10 to the power 3 Newton. And then your moment is going to minus 16 times 10 to the power 3. Okay, your moment is minus 16 times 10 to the power 3 Newton. Right. Okay. So once we are going to test z equal to 0.8. So now I'm going to bring in the values of the geometry of our cross section. Oh, where is it? Yeah, this one. Okay. Okay.